Okay, back for part two. Hopefully you tried it on your own. You didn't peek and cheat. That just spoils the wonder, spoils the discovery. So, but there they are. Okay, first two don't work. And hopefully, for whatever you picked, as long as you put it into your calculator, right? The these two work, and then this one works. That one doesn't work. So these are actually these three are our new today's new log laws. Um, and does it make sense? It doesn't appear to be, right? Why would be when I take the log of a product of stuff, why would it be adding on the outside when I split it up? Why does that make any sense? Well, if we think about what a logarithm actually is, it makes a lot of sense because what is a logarithm? A logarithm is the exponents, right? So what's this saying? When I have two powers, when I have two powers, two inside things, two powers, two values of y, we could say this, and I want to simplify that, well, what I can do is I add the logarithms. I add the exponents. When I'm taking the product of two powers with the same bases, I add the exponents. We learned that back in grade 10 or 11. So this is kind of like a grown-up grade 12 logarithm version of this very thing. And the other two are also very, very similar. Now, notice that this is kind of an argument why it makes sense. When I take two powers, um, then I subtract the exponents. You know, when I have a power of powers, I multiply the exponents. This one kind of looks like this, by the way. What I have here is I have a power, a to the exponent n is a power, and then I have a power of it. Well, what do? I multiply the exponents, right? I multiply the exponents, thinking of the logarithm of something as an exponent. How we actually use this logarithm rule is we can just see, well, if we got this sort of thing, the n can be written down in front, and that's going to be nice. Um, these sort of calculator investigations that we did, of course, we got 40 people or something like that in class. If we had 40 people picking 40 different values of these variables and all getting the same answer, is that a proof? Is that a proof that we've actually got a law? And hopefully you realize that no, yeah, it's good evidence, maybe good evidence that it's probably always true if it's happened 40 times, but it's not a proof. And we want to do some proofs. And I know you're getting sick of proofs, but this will be good practice for us. Again, if I want to prove something, I'm doing F. The other two are very similar. I'm going to break it into its left side and right side, and I want to somehow turn this into this somehow. Okay. And basically, what we're going to do, and this isn't a fantastic proof, but at least it's a way to make you, I think, believe that these are true. Um, we're basically going to lean back on what we know about exponent law. So I'm going to say let big M be a to the exponent x, and I don't know what x is. X doesn't appear anything here. I'm just saying m is some power of a, and we could figure it out, I suppose, if we were lucky, but we're not going to need to. And this is a to the exponent y. So I'm writing m and n as some powers of a. We don't know. Okay? So what does this look like? Well, I'm going to substitute. I'm going to use this idea and substitute right in here. So m is a to the exponent x, n is a to the exponent y, and can we simplify this at all? Well, yeah, we can, because we're good at this part inside, right? This is just a exponent law from back in the day, back in, I don't know, grade 10, whenever you learned this. Two powers with the same base, I can subtract the exponents. So I have a to the exponent x minus y. Okay. Well, now what do I have? See what I got now? I got a function composed with its inverse. Log base a to the exponent. What happens is that these two things sort of cancel each other out. And what am I left with on the left side is just x minus y, these two exponents that I don't really know, but I don't really care what they are either. All right, so somehow I've got to get this to work into being x minus y. Can I do it? I hope so. Now I'm going to pull the same trick. That m is just a to the exponent x. This subtract gets written down. And my pen's being a bit glitchy, so hopefully you're being patient about that. N is a to the exponent y. And then what do I got? I got two things there. Function composed with its inverse, function composed with its inverse. They cancel each other out. I'm left with x. Copy down the minus sign. Function composed with its inverse. Left side equals right side. Got it. And the other proofs are very similar. One thing you can do, especially if you know you're headed towards math or engineering or something like that at university, is you should try these proofs. Okay? Prove, don't like the glitchy pen. Prove property E and G. Okay? Try those. See if you can, very similar to that one. All right. Dandy. Now, some homework type questions. It says rewrite using log laws. So this is kind of a strange question. It's not prove anything. It's just change the form using the log laws. Well, which one does this look like? I don't have two things on the inside, so which one does it kind of looks like this one, right? I got something out front and then a logarithm. Well, what can I do if something's out front? I can actually put it up in the exponent. So if I just want to change the form, just rewrite. What's this doing? Go away. No, no, go away. Okay, good. Then it's a sort of can be written up there, x to the exponent a. Just change the form. Just change the form. Notice here we've got all the same bases. The base is m. That means I can use my log laws. Well, what one does this look like? This looks, there's two of them here actually, right? I've got one of them where I got two logs added. Two logs added, and that means it becomes multiply on the inside. So when I put those two together, same base doesn't change, and then on the inside it becomes multiply. Now, I left a little room here because this subtract log base m of z, well, that's kind of this one, right? When I subtract logs with the same base, I divide the powers, so that means this one's going to be over z. See, in this part, maybe I can do in my calculator, right? Maybe. Right. And these rules we can actually get used to evaluate a whole bunch of stuff. Now, notice, wouldn't we love it if it was base 10, because we could just jam all this into to our calculators? Well, we can't do that, right? We can't put in log base 2 of 3.2, but I can use a log rule. The log rule here is when I'm adding two logs, that becomes multiply on the inside. So this is 3.2 times glitchy pen. Oh, I hate the glitchy pen. I hate the glitchy pen. It makes it look so nasty. All right. Here. 2, and then that times sign. There. And what's that? That's 32. Still can't put that into my calculator, but 32 is a power of 2. These are the ones we were doing yesterday. Can I write 32 as a power of the base? Yeah. And then I could think of this coming down out front, or a function composed with its inverse cancels out. I think you won't be surprised by the answer is 5. Same thing here. Two powers with the same base, but I'm subtracting the logarithms. That means I can divide the power on the inside. Trying to write slow enough that my pen doesn't glitch out. All right. This I'm going to do in my head. That's 125. And again, I can write this, the power, with 5 as a base, and then I'm going to have a function composed with its inverse. And what's the overall answer? 3. Notice I have not reached for my calculator once yet. Okay, what am I going to do here? Well, there's a couple different ways you could approach this, but if we're using a log rule, this has got to go up this way, right? So I could think of log base 4 of 2 to the exponent 8, right? And if I wanted to, I could put that into my calculator. I get some big long number. I don't know what it is. What's 2 to the exponent 8? We count by 2. 2 times 2 is 2 times 2 is 4. Then times 2 is 8, 16, 32, 64, 128, 256. I could write that as 256. But then what's 256 as a power of 4? Geez, I don't know. I'm going to have to reach for my calculator. But let's be smart here. Why not? Let's be clever. And by the way, this technique using your calculator would be just fine. But I want to be smart. This, notice, if I could make this a 4 in here, then it would be a function composed with its inverse, right? And I know 2 squared is 4. I also know when I have exponents on exponents that I multiply the exponents. So what would this be? This would be a 4 here. So this is 2 times 4 gives me the exponent 8. This is 4. 4s are going to be wild here in a second. Base is 4. 2 to the exponent 2 is 4. Function composed with its inverse, the whole answer is 4. Dandy. What do we got here? Starting to look nasty, some of these. Notice that I've got log base 7 and exponential function base 7, and they're almost composed with each other. They're not quite, though. They need to be right next to each other, right? And then if I had something here, then these would cancel out, but this negative 2/3 is in the way. Let's use a log rule in the exponent. You see how this is just, it's kind of like this one, right? But in the exponent, the 2/3 is out front of a log. It can sort of go up there. And that's how I'm going to approach this one. 125 negative 2/3. Oh boy. See, there's the function composed with its inverse. And I could cancel that now if I wanted to. And then what does the question become? It becomes a grade 11 exponent question. Yeah, I'll go through and I'll remind you of what this. Remember, negative exponent means 1 over. The bottom number is the root. And the top number is the exponent. So this is all something squared. I'm running into my homework cloud, so can I go sideways? No, I can't. I'm going to have to squish. Want to do the cube root first. Make the number smaller before I make it bigger by squaring. Again, I haven't reached for my calculator yet, so nor should have you. Cube root of 125 is 5. That's squared. And the answer in perfect form is 25. Now, can I put that into my calculator and just get 1/25th? You need to show the steps. You need to show that you understand what the exponent rules do, okay? Should you do that to check? Absolutely. You can use your calculator to check. All right, what do we got here? This is easy peasy, right? The 2 comes out front. A function composed with its inverse. This is just 2 times, and what's a function composed with its inverse? That's just 1, right? I'll write it out again just so we see it, but log base 4 of 4, that's just 1. This is, by the way, we got two logarithms, base 8. Notice that even if we couldn't evaluate this one earlier, I couldn't have put these 2 together because they have different bases. So there's no rule going on here. And in fact, if I look carefully, this was meant to be a little bit of an eye-opener here. This isn't log base 8 of 8. What's the rule when I'm multiplying 2 logarithms? So I have log times log. Notice this is log plus log, log minus log. This is n times log, not log times log. So what's the rule here? Where to go, where to go, where to go? What's the rule here? There isn't a rule. There's no rule here. I can't simplify this. So let me write that in there. Can't simplify. And excuse the glitchy pen. The reason is there's no rule. There's no rule for that. So how do I actually handle that? Do I just cry and quit, or quit and cry, and whatever order suits us? No. I can write 2 actually as a power of 8 because 2, that 2 there is the cube root of 8, isn't it? So I'm going to write log base 8, and since, where can I write this so we'll remember? We have 2 cubed equals 8, so then therefore 2 is equal to the cube root of 8. And remember, fractions of fractions in the exponents means roots. So I can write that as 1/3. And similarly, well, then what's a quarter? Or sorry, what's 4? It's just this thing squared. Therefore, if I square both sides here, 4 is equal to 2 squared, which is equal to 8 and 1/3 all squared. Multiply the exponents, right? This is like 2 over 1. Multiply the exponents. This is 8 to the exponent 2/3. These exponents business is a little bit tricky, but you did see them in grade 11 as well. So this becomes 4 is just 8 to the exponent 2/3. And notice now I've got a function composed with its inverse twice. Bam, bam. The exponent comes down. I'm left with 1/3. The operation in there is times still. Times 2/3. 2 plus multiply across, right? Just the fractions. 2/9. 2 and 2/9. Done. All right, that's it. Lots of little bits, and it looks like a million questions of homework, but they're all teeny-weeny ones like this. That's it.